Let's go on to speak about the electrical driving force. And so the electrical driving force really has to do with charged particles and the separation of charge. So let's speak about some terminology here that will be important for understanding this force. So first of all, we want to think about what an ion is. An ion is any charged particle. Sodium is an ion, potassium is an ion, calcium chloride is an ion. And then more specifically, we have cations and anions, right? And this should be a bit of a review here, but cations are positively charged particles. So again, sodium is a cation, it's positively charged. Anions, however, are negatively charged particles. So chloride is an anion because it carries that negative charge. So this is important in determining the electrical driving force, right? The type of charge, whether it's positive or negative, whether it's a cation being moved or an anion being moved. Another thing we want to describe here is the membrane potential, what the membrane potential is. And this is really a force. It's an expression of a force that's created because of the unequal distribution of anions and cations across the cell membrane. In other words, it's the separation of charge. Okay, the fact that we have, let's say, more negative inside the cell and more positive outside the cell. Once again, because we have different proportion of different ions. So the outside of the cell is more positive because we have an excess of cations on the outside of the cell. The inside of the cell is more negative because we have an excess of anions on the inside of the cell. And so that separation of charge, that differential, if we will, is what the membrane potential is. It's a force that is created because of that unequal distribution of these charged particles. And so what the force really wants to do is move those particles, right? Like charges will attract, opposite charges will attract and like charges will repel. So there in and of itself is this electrical force that we describe as the membrane potential, okay? We also want to think about the magnitude of the membrane potential. How strong is that force that wants to attract or repel those differing charges? And so this is how we express the strength of that membrane potential. And we usually do so using millivolts. And when we do that, we want to reference the inside of the cell with respect to the outside of the cell, okay? So I'm just going to quickly illustrate here at the bottom that if we have a cell, all right, we've got more negative charge in here, more positive charge out here. Then what we have is we're describing the inside of the cell with regard to the outside of the cell. And so the strength of the negative charge inside of the cell is what we represent as the membrane potential. And so I can say that the membrane potential here is equal to, let's say, -70. And again, we're representing this with millivolts to represent that strength, -70, excuse me. And what this -70 means, again, referencing the inside of the cell, is that the inside of the cell has a -70 millivolts of a differential with respect to the outside of the cell. In other words, the inside of the cell is -70 or more negative when compared to the outside of the cell. Okay. All right. So here's probably a better illustration of that. So we have a plasma membrane that's separating two fluid compartments here, the extracellular fluid compartment in blue and the extracellular fluid compartment in blue, and then the intercellular fluid compartment here in orange. And so what we see is that there's an excess of anions on the inside of the cell. There's an excess of cations on the outside of the cell. And so this is what we mean by the membrane potential, the separation of charge across this membrane. It's going to create a force where these negative charges want to get over here. These positive charges want to get over here. And so that's another force that wants to move particles across our membrane. And when we describe that membrane potential, we usually reference the inside of our cell. And so saying that there's a -70 millivolts of a membrane potential really means that the inside of the cell has -70 millivolts worth of charged particles with respect to the outside of the cell. Okay, let's continue on here describing the electrical driving force. So the principle here, again, the opposite charges will attract and the like charges would want to repel. It's also going to depend on two factors, the polarity of the cell. So again, that negative, positive, inside being more negative, outside being more positive, that's what we mean by that polarity, as well as the charge on the particle. So whether the particle itself is positively charged or negatively charged, okay? And again, just we'll describe this here in a little bit, but think about a negatively charged particle. Where would it want to go? It'll want to go to the positive charged area. So a negatively charged particle like chloride wants to get to the outside of the cell because the outside of the cell is more positively charged. And so that's what we mean by the direction of the force depends on the polarity of the cell, where has more negative versus positive, and then the specific charge on the particle in question, and that will guide whether it wants to go to the positively charged region outside or the negatively charged region inside. Okay. I apologize, my pointer is not cooperating. Okay, so let's illustrate that here once again. So now we're looking at our electrical driving force, and we're going to spend a bit here sort of describing it in detail. So we said that this is a force, again, wanting to move particles across our membrane, and this force depends on two factors. First of all, it's going to depend on the charge of the particle in question. Okay. And then I'm going to put in brackets here, whether it's positive like sodium or negative like chloride. Okay. The second thing that it's going to depend on is the polarity of the cell. Okay, the polarity of the cell. And this is really going to be determined by the state of the cell. Okay, whether the cell is excited or resting, and really which area of that cell, whether it's the intracellular compartment or the extracellular compartment, that has the excess in positive or negative charge. So again, the state of the cell, whether it's predominantly positive or predominantly negative. So these two factors will determine the direction of the electrical driving force, what direction those charged particles want to move in. So again, very simply, let's kind of draw a cell here. And first off, we're thinking about a resting cell. Okay, and so a cell at rest is more negatively charged inside. So let's put those anions in. So we've got excess anions on the inside of the cell. And you want to think about an ion like chloride here. And then very few anions outside. Let's draw in our cations. So excess cations on the outside of the cell. And very few cations inside. And again, we're thinking about a charged cation, charged ion or cation here, like sodium on the outside. Okay. And so very similarly to the way we described for the chemical force, we can think about what direction our two particles would likely want to move in. Okay. So this chloride would likely want to get to the outside of the cell, right? Remember, the opposite charges attract. And so there's more positive outside here. This is the positive area, if you will. And so a negatively charged ion like chloride is really going to be, wanting to get outside here. That force is going to be driving this anion to the outside of the cell. Okay. So let's draw that in here as well. So there's a strong electrical driving force trying to move chloride to the predominantly positive area. On the other end, there's a strong driving force that wants to move an ion like sodium on to the inside of the cell where we have more of that negative charge. Okay, so I'll just write here in just a little asterisk here that opposite charge attracts, like charge repels. Okay. And so this is what we mean by that electrical driving force. It's a force based upon the charge of the particle, as well as the polarity of the cell. Is there excess negative? Is there excess positive? And so it wants to move the particles to the opposite area where those opposite charges can attract. Okay, let's think about an excited cell. So this is kind of slightly flip-flopped for an excited cell. And so an excited cell actually has more positive charge inside. And we'll talk about how we excite a cell later on, but let's do this. An excited cell has more positive charge inside and a little bit of positive charge outside. And then it's got more negative charge on the outside and a smaller negative charge inside. Okay, and so again, thinking about our two ions here, chloride and sodium, where is chloride going to be trying to get to in this scenario? Where is our electrical driving force going to try to move chloride in this scenario?
Inside the cell.
Perfect, thank you, inside the cell. I'm just gonna write at the bottom here an excited cell. So yes, that's gonna want to move chloride onto the inside of the cell. It's a negatively charged particle, there's more positive charge inside, and so chloride wants to get inside of the cell. Okay, and then alternatively, sodium is going to be moving to the outside of the cell. Where we have more of a negative charge. Okay, I hope that's clear. I'm gonna pause a little bit and see what questions we have. And then we'll keep going.
So is that because it wants to travel from a high to a low concentration?
I'm glad you raised that question, and the answer is no. We're only taking into account the electrical driving force, so you're still considering the chemical driving force, and eventually we're going to put those two things together, but for now, and just in this context, the electrical driving force does not move particles according to concentration gradient. It only moves the particles according to their charge and the polarity of the cell, looking only at the electrical driving force. Okay, I hope that made sense. So it has nothing to do with the concentrations, only has to do with the polarity of the cell, whether it's excited or resting, whether the inside's more negative or positive, and then the charge on that specific particle. Okay. And there's this really nice video that kind of summarizes this. This I'll put into Brightspace. If it's not already there, I'll embed this into Brightspace so you can check this out when you look at the notes there. Okay. Now, the next thing we want to do here is think about the magnitude of the electrical driving force. And so the electrical driving force, we said, can be graded, right? It has a certain strength to it. It can be really strong or it can be really weak, and that will depend on some other factors here. So let's talk about the magnitude or the strength of that electrical driving force. So this is basically the strength of the membrane potential which we describe in this way, Vm. And again, just to really describe this here, the strength of the membrane potential is how strong is that force? You can have a small force or a weak force where the particles, want to get over to the other side, or we can have a really strong force where the particles really want to get to the other side. So there's some gradation in terms of how strong that force is that wants to move those particles. Now, the strength will depend on the amount of charge. Actually, let's write that out in full here. So the strength depends on the amount of charge, right? We can have different amounts of charge, amount of charge and type of charge on the particle in question. Okay, so essentially whether it is a cation versus anion, as well as whether it is divalent. A divalent ion has two charges, like calcium, or, let's put versus, a monovalent ion, right, which only has one charge, like sodium. Okay, so these things will determine how strong that charge is. And so if we have a cation, it's positively charged. If it's a divalent cation, it's going to have more of a charge, more of a pull, more of a stronger driving force than if we compare it to a monovalent ion that only has one charge. So let's kind of illustrate that here at the bottom. So we've got three scenarios or three cells here. Okay, let's think about the membrane potential in each of these. So the membrane potential here is negative 60 millivolts. And so let's think about our charges here again. So we have negative charge inside the cell. Remember that negative 60 millivolts is referencing inside the cell. So that means that the inside of the cell is negative 60 with respect to the outside of the cell. So we've got negative inside and positive outside, okay? And so we wanna, let's complete this one. So let's think about an ion like sodium. So sodium wants to move into the cell because of this separation of charge, because the inside of the cell has a negative 60 charge, and because it wants to get to this negative environment. Okay, let's look at another scenario here. So the membrane potential here is negative 120 millivolts. And so sodium really wants to get into the cell, right? And so that means that there's a stronger negative charge inside the cell. Stronger negative charge inside the cell, and then a stronger positive charge outside the cell. So there's a stronger separation of charge, okay? And so naturally sodium, it doesn't just kind of want to get into the cell, it really wants to get into the cell, okay? There's a stronger force here. And that is also reflected in the number, in the value. The value is twice the size as it was here. So that is showing us that there's a stronger magnitude of that force, or there's a larger strength to that driving force. Let's look at an example of a divalent cation movement. So once again, we have a membrane potential of negative 60. So very similar to what we had in the first scenario. So our membrane potential, negative 60 millivolts, which simply means that we've got that sort of standard separation of charge. We've got negative charge inside and positive charge outside, okay? And so what we see here is that there's a stronger movement onto the inside of the cell. Because we have a divalent cation. So whereas the membrane potential is the same as it was in our first scenario here, the strength of the driving force is much stronger. It's twice the amount or twice the magnitude, simply because of the divalency of this cation, right? Calcium, excuse me, I can't speak today. Calcium has two charges on it. And so having two charges on it, it really wants to get into the negative environment in the cell, all right? And so this is what we mean by the strength of the driving force depends on the amount of charge. Okay, so whether it's divalent or monovalent, that's going to determine or dictate the strength with which that ion wants to move. Even if we have a very small separation of charge, as well as the type of charge. If it's positive or negative will determine where it wants to move as well. If we were considering an ion like chloride here, chloride would be trying to move outside the cell, okay?